Let's delve into the core missions driving the PREDA team. Our first mission is to envision a future where gas fees are down to nearly zero. Secondly, we aspire to truly scale out top-tier smart contracts, and I'll elaborate on some of these contracts shortly. Our third mission is to extend the reach of blockchain techniques beyond financial applications, exploring their potential in various fields. Lastly, we aim to boost blockchain techniques in areas currently dominated by Web2 giants. Efforts have been made to transcend the limitations of a single computer by implementing multi-instances of virtual machines across multiple computers, a prime example being the sharding technique. In this approach, each smart contract resides in a dedicated shard, complete with its virtual machines. While these methods enhance overall throughput and enable seamless smart contract migration, it's crucial to note that, from a smart contract perspective, all its transactions still operate within the constraints of a single virtual machine. Polkadot, Cosmos, Near, Zilliqa, and several other platforms are successful implementations of using multiple instances of virtual machines, utilizing terms such as parachains, multi-chains, or multi-shards. How about the Ethereum network Layer 2 rollups? Well, they still fall short because individual smart contracts remain confined within a single virtual machine. PREDA's innovative approach involves running a single smart contract across multiple virtual machines. The methodology comprises two key steps: first, deploying each smart contract on all virtual machines, and second, dividing and distributing the processing of their transactions AC. Through our mechanisms, every smart contract gains access to the processing capacity of the entire network, resulting in boundless performance, shared liquidity, and consolidated staking values. PREDA presents a new way to develop a smart contract, by state partitioned across multiple virtual machines and algorithm decoupled from data dependencies. The result is a natural and efficient parallelization and distribution of smart contracts across the entire network. PREDA is about how data is defined and hosted, how data is accessed and updated, and how code is described and executed. It is not a language that may concern about actual syntax and grammar. Currently, it is implemented as a new language and an extended Solidity to demonstrate the PREDA programming model is working. The PREDA programming language is now in production and is used for the hackathon. The figure shows a simplified ERC20 smart contract code in Solidity and in the PREDA language. The PREDA code looks largely the same as that in Solidity. The differences are: 1. User balance is defined as a map in Solidity while defined as an address variable in PREDA, and 2. The workflow of fund deposit in this case is defined as a relay. The PREDA programming model can also be implemented by extending Solidity and then support CVM compatibility. This is experimental right now, and we are actively working on that. In the realm of computing systems, developers' focus lies on the interplay between code and data. In programmable blockchains, this translates to transaction functions and contract states within smart contracts, modeled as a state machine. A state machine typically resides in a virtual machine, encapsulating both code and data, and that enables sequential execution of transactions with the entire dataset available to any section of the code. In PREDA, with multiple virtual machines, our objective becomes leveraging the combined potential of all available VMs to support a smart contract having massive transaction traffic. In the PREDA model, we take a novel approach to contract states by dividing them into numerous non-overlapping pieces. Each piece is exclusively hosted in a designated VM instance and is indexed for easy retrieval. The complete code of a smart contract is fully replicated across every VM, ensuring that any transaction function can be executed on any VM instance. Then, transactions related to a single smart contract are distributed to different VMs for processing and updating, based on the pieces of contract state hosted by which virtual machine. This methodology allows a smart contract with substantial transaction traffic to be collectively processed by all VMs in the network, with its contract states distributed among these VMs. As the number of VMs increases, the scalability of a smart contract extends to meet the demand for transaction throughput and contract state memory storage. Let's look into the details of the PREDA programming model. We will introduce two key features: functional relays and programmable scopes. In real cases, a complete transaction logic may require access to different pieces of contract state which is located in a different VM, even for simple applications like payment. With the architecture we just talked about, the transaction executing in one VM will reach a point that requires access to an external piece of contract state that is hosted by another VM. In the PREDA model, such case will be converted to an asynchronous relay toward the VM where the required piece is located, along with function context to resume the execution. The relay transaction will be picked up and trigger the execution of the rest of the transaction logic in the VM where required piece of contract state is hosted. Let's look into a payment case in PREDA. Bob wants to transfer some tokens to Alice. Bob's balance, as the contract state, is stored in one VM, see VM number 1, and Alice's balance is stored in VM number 2. Bob first initiates a transfer transaction. That will be processed by VM number 1, and Bob's balance is updated by minus the amount of token. VM number 1 doesn't have Alice's contract state. Then, a relay transaction is emitted after the execution of minus. The relay transaction will be executed in VM number 2 that has Alice's balance data, and the amount of token will be added to Alice's contract state. Beyond the toy example of payment, the relay execution mechanism supports multiple relay emissions in one execution and multi-hop relays, so that general smart contracts can be implemented using the PREDA model. Programmable scopes provides a flexible and intuitive way to customize the partitioning scheme of contract states. As in this example of the simple payment, balances of all users are defined as a scope indexed by address and each value is a bignum to store the amount of the owning token. This basically partitions the states of the smart contract into a great number of pieces, one address each. Every piece can be deterministically assigned to a VM with a mapping function from address to the index of the VM. Such scope can be indexed by other type of the keys like integers or hashes by specifying different data type after the @ mark. This provides the flexibility to different algorithms. Note that every transaction function in PREDA also has a scope indicator. In this example, the transfer function is defined in an address scope. When the function is invoked, the current address is provided just like the this pointer in C++. In this example, it serves as the payer of the transfer. That's why, there is only payee explicitly declared as the function argument beside the amount. Within the function has immediate access to any states of any smart contract, but only the piece of state of the current address. It is enough to make the withdraw. Then for performing the deposit to the payee, a relay is emitted without assuming which VM is hosting the balance of the payee. The address payee will be provided as the current address when the relay function is executed in the destination VM. Restricting the data access pattern of any function within the current scope is key to decouple data dependencies, so that a smart contract can be inherently parallelized and distributed across a large number of VMs. In most cases, a straightforward approach of writing a PREDA smart contract works. In some cases, a good partitioning scheme should be carefully designed. There are several considerations of a good partitioning scheme. First, because a relay transaction takes additional overhead on bandwidth and memory, a good partitioning scheme should minimize external data dependencies. Secondly, fine granularity can help to well-balance transactions to VMs, especially when there are a large number of VMs in the network. Thirdly, a good partitioning scheme should be neutral to the actual architecture and configuration of the underlying blockchain system. For example, don't assume the number of VMs available. The PREDA model makes no assumption on mapping from different types of scope keys to the VM index, except it should be deterministic. In some cases, there are a small amount of contract states cannot be partitioned or distributed in different VMs, which is required in every transaction like global configurations or parameters. Or, some decisions should be made by aggregating information of the entire network, like summing up votes to reach a global synchronized result. Unlike state piece distributed in VMs, global states are duplicated and synchronized in all VMs and are available for immediate read by functions executing in any VMs. Any transaction updating global states will be executed in every VMs in a consistent order to keep global states synchronized in the entire network. Here's an example involves different types of contract states. The votes in global scope represents the total number of votes accumulated from the entire network, and the valid period of the voting process. Here local scope is a scope for separated states located in each VM, which will not be referred by other VMs. In this case, it serves as a temporary accumulator of ballouts within a VM before gathering to the global scope. In address scope, the state last _ballout records the timestamp of last vote issued, to prevent duplicate voting. The ballout function will be invoked many times because each address gets a chance for one vote. It makes no relay emission since the ballout is accumulated in the local state of the current VM. States in global scope can be immediately accessed for reading by function executing in any scope and VM. In this case, the global voting period is used to ensure ballouts are made in desired time windows. A function executing an address scope implies a specific instance of VM. The local state of the VM can be immediately read or updated from the function. In the case, a single ballout is accumulated in the local state of the VM before being gathered to the global scope. When voting period ends, the gather function will be invoked in each VM to gather all accumulated ballouts in each VM to global. A relay to the global scope from each VM will be emitted for such gathering. In an ideal implementation of the PREDA model on a sharding blockchain, identical global blocks and different shards blocks are executed interleaving. That means an identical global block including global-only transactions is executed first in each shard, and after the shard blocks having different set of transactions dealing with states belong to each shard are executed. If implementing the PREDA model in a L2 system, global transactions should be duplicated in every execution queue by sequencer. Let's go over the language itself very quickly. The PREDA language is like JavaScript or C for statements, declarations, expressions and flow controlling with slight modification and extension. As shown in the figure, you can find the PREDA language has additional built-in types as begin, token, address, string, and array. The PREDA language has several coding restrictions. They are defined clearly in the PREDA language specification and you can download the specification from our website.
Our built-in types are mostly value type, but there are several reference types like string, struct, array, map, and token. Integer comes with explicit bit width specification and begins is signed big integer in PREDA and a variant-sized variable from 64 bits to 8192 bits. High precision floating point number with deterministic consistency is defined in PREDA. The code snippet shows an example to use our float type to calculate the value of by. Our address type uses 36 bytes, including 32 bytes for actual address plus 4 bytes to encode the algorithm label and checksum. In PREDA language, scope modifiers are used to specify the scope for every state variable and contract exported functions. The default is global scope. We also define how different scope functions can immediately access a scope-defined variable in a smart contract. We use the keyword import for cross-contract invocation. We also implement two context variables in the PREDA language to provide information of the transaction and the block being executed. The relay statement can be implemented as a lambda function. It corresponds to a relay transaction that allows execution logic involves multiple addresses, likely in different shards, to be accomplished step by step. Recurrency is allowed. As shown in the figure, relay microtransaction number 2 is emitted in relay microtransaction number 1.
In PREDA code, we provide C++ transpiler to translate PREDA code into C++ code as an intermediate code. Then developers can use native C++ compiler to generate native binaries for native execution, or use WASM compiler to generate WASM bytecode for WASM engine. We implement a VS Code plugin for source code editing with syntax highlighting and IntelliSense. We also define and implement testing script for automated test of PREDA smart contracts on the simulator. The testing script supports transaction generation, direct contract state modification, and performance profiling. The beta production of PREDA is released on our website and you can download all materials there.